Hello everybody. A bunch of people asked me how to write Solana programs in assembly, actually. And my setup is a little bit bad. I'm currently still in Koh Samui for Island DAO. But you can actually write a Solana program, like a counter, that only uses 4CU. And this is what we're going to do today. And first of all, I'm going to guide you through all the resources we have on that. So there is this optimized CUs in programs repository here on the Solana devs. And it shows you a bunch of things that you can optimize, especially in Anchor programs. Here you have a macro on how you can profile how many CUs certain calls actually cost. Then you have, you can see that logging is very expensive, how you should handle different data types, you shouldn't need too many allocations, and how you can do serialization, also with zero copy, and that you should definitely cache your bump of your PDAs because it's very expensive to do that. And so on and so on. But today we're going to look at assembly. And here you can already see that these assembly programs are extremely small. Like you can deploy it in 2 transactions. And the counter only takes 4 CU. My first iteration was 6 CU, but today we're going to write it in 4, hopefully. And in general, I would probably not recommend write your programs in assembly, since it's it's very difficult. It's not very secure. You need to do all the checks yourself and so on. And Anchor does a lot of security checks, and even in native, you at least have over and underflow checks and so on. But you can do it, and I want to show you quickly how this can be done. So the first option is you can do John Chinque's assembly tools. You can find the link in the CU optimization repository. And here you install your LLVM tools, then you go into this hello world example, and then you have a make file that creates the SO file, and then you can run these tests on it. And the tests are written using bank run, so you don't actually need a local validator for it, which is pretty nice. But what we're gonna use today is actually the SBPF assembly tools that Dean wrote, which are super nice. If you want to do anything with assembly, I recommend you to follow Dean on Twitter as well. I think you can, let me quickly show you his profile, because he does, I think, most of the assembly stuff. His first entry here already. So this guy, he's great. And he built these assembly tools, which make it super easy to get kickstarted with assembly programs. So basically you have SBF init, build, deploy, test, and so on. And we're gonna use these, but first I want to show you a few more resources that we have. So the first thing you probably need to do is probably read through these things. So in assembly, you basically just get a byte array with all the instruction data and all the accounts, and then you can do stuff with it. But on the first try, you will probably have no idea what's in these bytes. So this one is very helpful. So this shows you, this is on the Solana docs page. It shows you all the input parameters that you get when you have an assembly function. So the first 8 bytes are the number of accounts that are coming in. And then you have, for each account, you have 1 byte that indicates if it's a duplicate, then you should definitely skip it. And if it's a duplicate, then you have 7 days of padding, so it's not super interesting. But then you have 3 flags for signer, writable, and executable. Then you have some padding, which actually the Rust crate for the entry point uses to save the original account data, as you can see here in the second link. Let me try to find the right spot. Here, DRI's account info. Here you can see it has signer, writable, and executable. And then here in this padding, it's actually saving the original data length of the account. So in case you're expecting this to be empty. Then you have the account public key, so it's just the account. Then you have the owner of this account. So in our case, this will probably be our program or the system program. Then we have unsigned 8 bytes that show you the lamperts of the account. So if you ever want to do a transfer, for example, then these would be interesting for you. Then we have 8 bytes that show you the size of the data account. So in our case, we want to do a counter. So we're gonna put in a U64, so it will be 8 bytes. And then you have X bytes of account data, and then you have 10 kilobytes of padding in case you want to reallocate your account. And so if you want to go to the second account, for example, then you need to basically put all these bytes here and then add another 10 kilobytes, and then you're at the second account. And then the last 8 bytes are the rent epoch. So what else did I want to show? So we have, there's also a Visual Studio Code extension that Dean wrote, which is super nice. You can just find it here in the extensions. If you search for SBPF, then you can install this and it makes your programming a little bit easier. Then there's a bunch of examples here. So there's a Fibonacci example and a soul transfer, for example. So this, wait, where are they? Here's the Fibonacci one. So it's very good to like have a little bit of a more complex program for you to look at to figure out how everything works. And if you want to use this to work with AI, actually it makes lots of sense to train it before you ask your questions on some of these examples. Then it will be way easier to work with. Here you can see, for example, for the transfer, it's this is how you would find the second account in your accounts array. And yeah, then it does a bunch of stuff. I'm gonna explain this on an easier example. Then yeah, we have 2 hello worlds in this repository. There's one written with John Chinquist's assembly tools and one written with SBPF. That's the example that we're gonna build in a bit. So I did it once before. I hope it's gonna work out. And if you want to do some real low-level optimizations, then there's a few more options. So you can play around with compiler flags. You could, for example, disable overflow checks, which is another thing I would definitely not recommend, but maybe in some cases this could be helpful. Then there's inline always and inline never. And inline always saves you some CU space, but it also needs more spec space. So, and recently I think there was an anchor bug which inlined too much things, I think when doing account deserialization, and then many people ran out of stack space. So yeah, but this is something you can also play around with to save some CU. And then there is non-standard heap allocators. So if you need like more heap space, like the standard heap allocator is a bump heap allocator, so it never frees up memory. So in case you need this, Metaplex is, for example, using smalloc heap in their metadata program. So this one will probably help. And there's another one that I saw which also frees up memory again, but it costs a lot of CU. So this is another thing you could play around with. And then there's different entry points. So the standard entry point of Solana is not necessarily perfectly optimized. And there's a few other options. So for example, you can use the Solana non-standard entry point by KV. And there's a few other ones. And you can read about these on these next 2 links. So this one is, for example, comparing these, and you can see unsafe rust, which is this non-standard entry point, saves a bunch of compute actually, and especially when using many accounts. So here in this comparison, you can see that for 64 accounts, while the normal entry points takes 10,000 CU, the non-standard entry point only takes 926. And then there's also another one called Pinocchio. But yeah, let's now go to write the program. So, but now let's start with the fun part and actually write the assembly counter program. So I already installed the SBPF tools from Dean. And now we have all these commands here: init, build, deploy, and test, and so on. So let's set up our project. So I opened Visual Studio in a new folder. And I'm gonna hide this. I'm gonna make this a little bit bigger. And now we're just gonna use SBPF init, and we call our thing counter. So that worked already, easy enough. Now we go into the counter folder, and I'm going to quickly show you through how this works. So we have a deploy folder, which you already may know from Anchor, for example, which has a key pair that's used to deploy our program. Then we have the source. This is our source, which prints hello Solana. And then here we have some tests using Mocha and Chai, I think. The first thing we need to do is we need to install yarn, otherwise we will not be able to run these tests. So yeah, I just install this and all this red stuff should go away. And here we can see we have a local connection and we have our transaction. So we send a transaction, we just put the signer, so that's one account, and our program ID, and then we send it off. And now let's see if we can run this. So we use sbpf build and sbpf deploy and sbpf test. And I'm first gonna run a new validator. So I open a new terminal and do Solana test validator. So that address is already in use. So let me quickly find where I have this already. Probably here somewhere. I mean, if it's already running, we can just use the one that we have already running. So we're gonna deploy this program, and then we have a success output here. And now we can look at this transaction, and we can see that we have printed hello Solana. So congratulations, that's already it. But yeah, the first thing I'm gonna do here is I want to always print out the logs, so it will be a bit easier. So I'm gonna do signature. And when we got the signature, we can use the signature to get the transaction. So we don't want confirm transaction, we want get transaction. And then we should be able to print this out. So this will be transaction.meta.log messages. So now if we run this again, we should be immediately seeing the output here. So we can see hello Solana. Okay. And yeah, now let's look at this code here. What's actually happening here? And it looks very tempting, I know. But if you get the hang of it, it's still tempting, but it's but it gets a bit easier. So first we have an entry point. This is basically our function where we get in all the data, like this big byte array with all the account data and the instruction data and so on. And then what we do here, LDDW means load double word. So what this does, it loads double word. A double word is 232-bit, so it's like 64 bits into register 1. Then the second thing it does here, it loads the number 14 into register 2. And then how function calls work, this is a syscall sol log. By the way, I'm not an expert in assembly by no matter, but how this works is that you have a function, and then if you want to call it with certain parameters, then the registered before it have to have the function parameters. So the first thing that we put in is the message, and the second one is the amount of the size of the message. And then here this thing row data means only read-only data. So here we have like all our constants. In this case, it's an ASCII string that says hello Solana. And now let's change this to hello devs. And so it should print hello devs. So, and we can see this is an access violation in program section 0xxx118 of size 14. So this is because now it's trying to read data that wasn't assigned to it. So in this case, it's now trying to read, I think, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are 12 letters, and it wants to write 14 and would then go into a memory that it doesn't belong to. So if we change this to 12, then we would actually now get probably hello devs. And if I change this now to 6, then we would only get hello, for example. So let's run this again. So now we can see it's only printing hello, comma. Okay, so this is easy enough, but now let's look at some other things. So as I showed you earlier, this is the byte array that is coming in. So the first 8 bytes is the unsigned number of accounts. So let's actually check this data in there and see if it's correct. So what we're gonna do is we load now the first 8 bytes of register 1, which has these, the whole account data. So what we're gonna do is we're gonna ld xw, so load extended word, and we're gonna put it in R2, and what we want to load is R1 plus 0. And then we're gonna do jump not equal 0, and then we go to an error. So what we are doing here is we are loading R1 into R2, into a new register, and then we check if this register is, I think it needs to be like this. If in register 2 we have 0, then we put an error. If it's not 0, we put an error. So we expect the accounts of this function to be 1, because we are putting in one account here in these account keys. And now we are checking here if the first 8 bytes in R2 are equal to 1, and otherwise we print an error. And this error we define here. And what we need to do an error in a Solana assembly program is we need to write the error code into the register 0. So we're gonna move 64, which means we are writing a value of 64-bit into the register 0 now, and we say we're gonna call the error code 1. I hope that works. Like I said, I did this once before, but I'm not sure if everything is gonna be all right. So now it says the account data is too small for instruction. So these SBLBF tools, they are not actually extending the program for you like Anchor does, for example. So what we need to do now is we need to extend our program. So I need to find the program ID, and then I'm gonna call Solana program extend program ID, and then just gonna put 1000 bytes. So now the buffer account for our, I don't know if this is the buffer account. Anyway, the account for our program is now bigger, so we can save, like upload a bigger program in there. So we're gonna build, deploy, and test this again. And now it's successful, and we are still printing hello, and we can see that our account number is apparently 1. So if we put this now to 0, then we should get an error, hopefully, saying that we are expecting a different amount of of accounts. And we can see that worked, so now we are getting an error. So now we made sure that we are calling this actually with one account. And now let's check something else here. So here we can see that for each account now, so we check these first 8 bytes. Now we can see for every account we have 1 byte that indicates it's a duplicate. So we don't have duplicates, so we can ignore that. And yeah, if it's not duplicate, then we can see we have these 3 flags here: is signer, is writable, is executable, and then some padding. And then we have the public account, the public key of our account, so it's just our account. And then we have the account's owner. This will be, in our case, either be our program or the system program, probably. Then we have 8 bytes of unsigned number of lamports. So if you ever want to do a transfer, then these 8 bytes are very interesting for you. You can find another examples of these of a transfer actually also in the assembly tools by John Cinque. So he did like a sol transfer which only takes 21 CU. So that's pretty cool. Then the next thing is interesting. So this is 8 bytes of unsigned number of bytes of account data. So this shows us how big our account will be. So in our case, we need 8 bytes. Because we want to save a U64 counter value, like a number. And then afterwards, we have the X bytes of account data. So and now we want to check actually if these 8 bytes here, the number of data that we have, the amount of the size of the data we have, is going to be 8 bytes. So we're gonna now write another one of these tests. So we're gonna load an extended double word into R3, and this is gonna be 8 for the accounts, then plus 8 for these flags, then plus 32 for the account address, then another 32 for the account owner, and then another 8 for the lamperts. And now in R3, we should actually have the data size of the account. So let's put this in here, and in our case, I mean, we're expecting 8, so let's do 8. But this will probably now throw an error because this account that we're putting in is the signer, and the signer has is a system data account, a system account, and it has 0 data. So now we can see that we get an error. Failed to attempt execute past end of text segment at BPF instruction. So it's probably just we are getting an error here now. So, and yeah, now we actually need an account. So we need now to create our counter account. So for that, we're gonna create an account. Actually, I'm not sure if this error is correct. Like failed attempted to execute past the end of text segment at BPF instruction. So let me quickly try to figure out what that is. Is this connected to the logging or is this something else? No, this is still. So I looked up the error. And I didn't run into this one earlier, so I looked it up here in the Solana RBPF errors and attempted to execute past the end of text segment actually happens when you exceed the maximum instructions allowed. And the reason for that is here we are running this error, but we are never exiting here. So when we do this error, we actually want to exit immediately afterwards. Otherwise, we are writing an error and then we are still trying to do other things. So if we, I guess if you already put like a 1 into R0, then you can't continue doing other things. So now I added this exit here. So after the error, when we run into this error, we will actually get an exit the program. So let's see if this works. Now, hopefully now we should just get this normal error. Yeah, so now we get error 0x. What we can also do is we can create another error so that we actually know what's happening. So we can call this error account data size. And now if we put this in here, in this error here, we just call another function basically, just in a normal programming language. Then here we can now see, now we are getting 0, 2 as an error. Okay, but yeah, this is still an error. So actually let's already put this here, like we are expecting 2 accounts. We need the signer and the counter, and we expect the counter to be 8 byte in data size. So now let's create this account and pass it in. So for that here, we need now another account. So I just gonna, it's difficult to use a PDA because a PDA, you would need to do a cross-program invocation to the system program to claim ownership of it. You can't just give it to, you can't just transfer any account to be owned by another program, because otherwise you could basically hack any DeFi protocol. You would just create an account which gives you like tons of money. So what we do is we create a new account. Create new account transaction. I mean, it's probably possible to do this in assembly as well, but I don't know how yet. So we create a system program account. So we need to import the system program. Then we have Lamberts and space. We want 8 because we want to save a counter. And for the Lamberts here, we want to actually use the correct rent. So account rent, and we can get this from the connection get minimum balance for rent exemption. So now we put these Lamberts in here. And then we gonna send this transaction. So I'm just gonna copy this over, and here we want to use the create new account transaction. And now let's run this. Oh no, first we want to also pass this into our program. So we're gonna use here our counter account. So let's rename this to counter account. This is now a new account that we create via the system program that has a space of 8, and then we pass it in here as a parameter. It will not be a signer. Does it need to be a signer? Not sure. Probably it needs to be a signer because we want to create the account. So let's leave it like that. And we will probably get in a, yeah, so now we are missing the signature for this key. So we need to add the signature, but here we have this helper function, and here we have the signer. I'm just gonna add the signer here as well, just additional signer. This will be a key pair. You can probably make this nicer if you're at home. And if you're just joining, we are building an assembly program, and we are currently putting in our second account so that we have a counter account and a signer. So we're gonna add this here, and we also gonna add this here, our additional signer. So now this should work, hopefully. So if we run this, so now if we have this counter account created and we can access this in the program and it worked, then now we will be able to change the data in this account. So, and as we learned earlier here, the next 8 bytes will be actually the bytes of account data. So we should be able to read the data, put it into a new register, increase it by 1, and then write it back. So that is what we're gonna do now. So first we're gonna read this register. So gonna load double word R4, and it's already recommending here me another 8-byte offset. Very nice. Then we're gonna add to R1, R4, this is wrong, I think. So we're gonna, what we want to do is let's first write a value in there. So we're just gonna use move 64 R4, and we're gonna put a 5 in there. And now we want to write it back. So, and for writing, you need to do to use ST. It's already recommending it here. So ST means for store extended double word. So basically we took now the account data, we put it into a new register, we set it to 5, and then we write it back. So let's see if that works. That seems successful, but we are not quite sure if it's correct. So what we could do now is we could write another one of these tests and see if this is actual 5. But what I would like to do instead, let's just get the account data here in the client and print it out. So we want var account data, and then we do connection get account info, and then we do console log account data. So now we are printing the account data after we increased it, and hopefully this should be 5 now. Let's see, this is 5. Yay, it worked. So we are actually already able to write data into an account now. So this is basically our account already. So, but what we're gonna do instead is add 64 1, and now whenever we call this, we are actually we are reading the value from the register at the account data position. We add 164 to it, and then we write it back into the same position. And so now if we call this again, it should be 1 because we're always creating a new key pair. But what we now could also do is we could probably just call this whole thing here again. Maybe, I don't know if this makes sense, but maybe let's try it out. Right here before this, we do another one. We call it transaction 2. Sign and send transaction 2, and now this should probably be 2, hopefully. Yeah, so now our counter is 2. Yeah, so congratulations everybody if you stayed this far. Yeah, this might seem like a bit weird to do. Maybe it's not really useful for many cases. I wouldn't recommend writing big programs in it. But for things like, let's say you have a DeFi protocol, and Dean had a very nice example at Breakpoint for this, and you want to make sure that there's no like MEV or sandwiching going on, or that a slippage is too high or something like this, then you could have a very simple transaction like this, which only takes a few CU, and make sure that the values that you're expecting are actually exactly what they are supposed to be. So for that it's nice. Or if you have like very performance heavy things that you need to do, like this Fibonacci example maybe makes sense. I mean, it maybe doesn't make sense to calculate Fibonacci numbers on chain, but yeah, you can do it. Whatever is performance intensive and you need like, or you don't have enough CU to do stuff, then you can like maybe take part of your code and put it in there, or you build a primitive that you reuse in multiple programs or so on. Yeah, definitely check out all the resources that Dean put together here and go through the CU optimizations repository. There's a README here. And yeah, optimize your programs. It makes things lots easier. Like you get better program inclusion in the block. And yeah, try it out. Maybe just have some fun with it. Like for me, it was super fun. Just trying us out and to knowing exactly where which byte is very refreshing. Like if you work with Anchor, maybe sometimes you have like macros and you're not exactly sure what is happening, and you have Borch serialization and so on. And here it's just you brutally put the data where it's supposed to be. Yeah, it's kind of nice. But yeah, be careful with it. There's no security checks and so on, like I already mentioned. Yeah, have fun and see you in the next video. Bye bye.